Triangle congruence, CPCTC. Our objective is to use CPCTC to prove parts of triangles are congruent. Why learn this? You can use congruent triangles to estimate distances. But what in the world is CPCTC? It is an abbreviation for the phrase corresponding parts of congruent triangles are congruent. Basically, if you've got two triangles that are congruent, all of its other pieces are going to be congruent as well. Let's look at proving corresponding parts are congruent. Okay, so we have one of our given here, and we know that this one was used because we have angle ABC is congruent to angle DCB. So it's the other one that we're looking at here. Alright, so we've got a side, an angle, and then we're saying, oh, reflexive property. So the reflexive property, the side that both of the triangles share, would be BC. So BC is congruent to BC. And now you have enough information to say, hey, the two triangles are congruent. But wait, this is generally where we would stop. We're trying to prove that the angles are congruent. Well, if your triangles are congruent, every other piece will be congruent. So the triangles are congruent by side, angle, side, which would mean that angle A and angle D are congruent. If we wanted to, we could say that BD is congruent to CA. We can state that angle DBC is congruent to angle ACB. The only one it was asking for, though, was angle A is congruent to angle D. So basically what you've been doing, just add a singular step to state your last piece and then say CPCTC. Because you have congruent triangles, so their corresponding parts are all going to be congruent. Let's look at another example using CPCTC in a proof. Okay, this time we're using it in the proof. So we have EG is congruent to DF. Why are we allowed to state that? Well, they gave it to us, so that's why we can say that. Now we have angle EGD is congruent to angle FDG. So we have EDG is congruent to FDG. So we have EGD. So this angle here in orange. And then we have FDG, which is this angle here. And now that you're looking at those two angles and we're dealing with parallel lines, what kind of angles are they? Well, they're alternate interior angles, so we're using the alternate interior angles theorem. Alright, well, we've got a side, or an angle. Now let's look at a side. And we have another side here. Alright, so we've got GD is going to be congruent to GD because both triangles share them. They have to be the same size, and that would be the reflexive property of congruence. And now we have enough information to state that the two triangles are congruent. Because we had a side, an angle, and a side, an angle, and a side. The angle was smushed between the two sides. So we are in fact using side, angle, side to state that the two triangles are congruent. Alright, well, since the triangles are congruent, all of the corresponding parts are going to be congruent. In the last proof, we stopped basically at step 6. So right after your side, angle, side, side, angle, right after the two triangles are proven to be congruent, you can then use corresponding parts of congruent triangles are congruent. Because if the triangles are congruent, all of the other pieces are going to be congruent. However, in the proof, we were stating, oh, well, we want the two sides to be parallel. Well, CPCTC doesn't give you parallel, it gives you congruent. So you want to go one step further. So if EDG is congruent to FGD, so we'll go with blue on these two here. So if this angle here and this angle here are congruent, what are we using to state, oh, well, that means that these sides have to be parallel? Well, we're using the converse of the alternate interior angles theorem because we're going from congruent angles to a set of parallel sides, so we're doing the theorem backwards. That's where the converse came from. And that actually concludes our lesson on triangle congruence with CPCTC.